always, sometimes never. If n is greater than or equal to 1, then the sum from 1 to n of I is n times n plus 1 divided by 2. It is always true. And we could actually prove it by looking at one of the other sums that you have done in the past and manipulating. But the purpose of this question is actually just to give us a little bit more experience working with mathematical induction. So let's do that. Our proof by induction will be the first thing I write. I always like to tell my readers my style of proof just so they get the right mind frame. Now, if this is a proof by induction, I know there are certain steps that need to be done. The first thing I need to do is show that this expression holds for the base case. In our case, it's the beginning, or where n is equal to 1. Then we would do our inductive step, which is to first write out the inductive hypothesis and then use it to show that if this expression is true for some natural number, it's going to be true for the next one. And then if I can show that the base case holds and the inductive step holds by the principle of mathematical induction, which I use PMI for shortcut notation, principle of mathematical induction, it would be the case that the sum I equal 1 to n of I is n times n plus 1 divided by 2. Now here what I did was I outlined my proof. And usually if I'm teaching a class and I want my students to prove something using mathematical induction, I will actually give them points for each one of these stages and each one of these steps. Let's go back now and fill things in. The base case, or when n is equal to 1. What do we want to show? We want to show that the sum I from 1 to 1 of I is 1 times 1 plus 1 divided by 2. So our proof is going to be to start with the sum I from 1 to 1 of I. Now what is that? Well, it's really only 1 point because we're starting at 1 and we're ending at 1. So since it's just 1 point, this sum is just this one term, and it's going to be 1 because we're summing I when I is equal to 1. Well, let's go back and see what we were trying to show. We were trying to show that this sum is 1 times 1 plus 1 is 2 divided by 2, which is 1. And so 1 is 1 times 1 plus 1 divided by 2 by arithmetic. And so we're done. The base case is obviously true. Now let's look at the inductive step. For our inductive step, the first thing I want to do is write down the inductive hypothesis. And that is that this expression holds for some natural number, I'll call it k. So I'm just going to write it as the sum from I equal 1 to k of I is, and again I'll just go up here, and when n is equal to k, that the sum is going to be k times k plus 1 divided by 2 by substitution. I'm going to assume that this inductive hypothesis is true, and I want to show that the sum I from 1 to k plus 1 of I also satisfies this expression, which means it would be equal to k plus 1 times k plus 1, which is k plus 2 divided by 2. So this is what I want to show. And I always write down my inductive hypothesis, and I tell myself what I want to show so I can do it. As usual, I'll start with my proof by starting with one side of what I want to show. And so in this case, I'm going to start with I from 1 to k plus 1 of I. Now, what do I know about that? Well, I know that it is 1 plus 2 plus dot 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 plus k plus 1. I can break it down into two pieces, the sum into two parts, and I can write it as the sum from I equal 1 to k of I plus the last term, which was when I was k plus 1, which is just k plus 1. And I can do this because all I'm doing is splitting off the last term. This is a strategy I often use. Now why? Because I know something about this sum. I know that this sum by the inductive hypothesis is k times k plus 1 divided by 2. And I always want to split my original expression into two parts where I can apply the inductive hypothesis. So now I know by the inductive hypothesis that what we have here is k times k plus 1 divided by 2 plus a k plus 1. Now I remember if I wanted to add two expressions, I need a common denominator, which would be 2. And if I perform some arithmetic here, once I have this common denominator, I can add the numerators, but now both terms in the numerator have a factor of k plus 1. When I factor it from the first term, I'm left with a k, and from this term, I'm left with a plus 2. And so the sum from 1 to k plus 1 of I is k plus 1 times k plus 2 divided by 2, which is exactly what I wanted to show. And so I'm done. Hence, by the principle of mathematical induction, it is always true that the sum I equal 1 to n of I is n times n plus 1 divided by 2. The strategy is to show that it's true for 1 in the beginning, the first one, and then to assume that if it's true anywhere along the way, it's going to be true for the next value in the set. And so therefore it's true for every value in the set. With natural numbers, in our case, 1 was the first value. And if it's true for 1, then it's going to be true for the next one. So it's going to be true for 2. It's going to be true for the next one. So it will be true for 3. And the next one, 4. Next. If it's true for 99, it's going to be true for 100. Then it will be true for 101. Then it will be true and so forth out to 1,000,000. Then it will be true for 1,000,001, and you get the idea. It's going to be true for all natural numbers.